been talking about musicians and psychoacoustic scientists and also mathematicians about these things, and been thinking about these things for a few years. So this is what came out of it. One short, maybe one short comment on what feedback came from the people that I talked to. So musicians were always kind of curious, but the mathematics was always way beyond what they really wanted to think about. They just wanted to do music. And some of the people who do music, they actually, I hope, think in these kind of terms, the things that I'm trying to model. Then I also talked about neuroscientists, and they were a little curious, but they were also thinking, well, what's the point of this? Because, well, they have been doing lots of studies and trying to figure out how music works, but they basically have a bottom-up approach to this thing. They take a little piece and then try to study that, and this is really a holistic concept. It's a top-down approach. I want to see what you can say about the music in general, about sound, but then about music. And so that was always a little difficult to talk to to neuroscientists. And then certainly the mathematicians, they also were kind of curious. And a lot of the mathematics is fairly, well, it's not that deep, I guess. You know, there's some nice things, and I hope certainly that eventually there will be things that we can talk about, that we can work on, that goes deeper into the mathematics. So those are a few comments up front. Let's just start with how music started. So the earliest recorded or the earliest known uses of music go back like 30,000 years ago. But only recently, really, 2000 BC, there was the first kind of music that was recorded like in music notation. Okay, obviously, I won't be able to tell what exactly it is, but this is called a cuneiform. It was found in Turkey, and that is supposed to be a music notation. But only very recently we have seen other kinds of music notation, especially when we were able to print these things. So here you can see some examples, and I guess 100 years ago you have the music notation that is very similar to how it is being done nowadays. So that's music notation. Music notation is really a big part of music theory, and music theory is what I want to, well, what I'm taking as a basis in order to construct this model. And what is music theory? Well, there is melody, harmony, rhythm, tuning, tonal systems, scales, chords, keys, notation, chord progressions, voicing, consonance, dissonance, and rhythmic relationships. A lot of things, most of which I won't be able to talk about today, but one thing in particular I would like to focus on, really, in a way, is music theory, like the functional harmonies. Some of you might know you have cadenzas, you have 2-5-1 or 1-4-5-1. Those are cadenzas. They are chord resolutions, and this picture looks kind of complicated. So my aim was to look behind the curtains and see where these rules came from. So the mechanism behind it. And some of you might know him. He's like a musical prodigy, he's a genius, some call him. His name is Collier, and he was asked what music theory is, or why music theory sounds good. Okay, there it is. Yeah. Sorry.
The question from Roy Woll. The question goes, why does music theory sound good to our ears? Is it science? Someone, please answer. I guess first of all, music theory doesn't really sound like anything. Music theory sounds like parchment. Music sounds like stuff though, and I guess the honest truth of the matter is no one really knows. It's a bit of a mystery.
And this is precisely where I'm thinking that mathematics can accomplish quite a good deal. eventually, maybe not just today. But this Jacob Collier guy, he really did some amazing things. So just let me show you one little piece, just 10 seconds. Oops, that was wrong. Yeah. Okay, so this is just a small excerpt. So what you might have realized, maybe some of you have realized, that the tune shifted a little bit. So usually you only have 12 notes, and he managed to, or rather he did this on purpose. He changed the whole tune to make it open up. And so he went in between the usual scale and really on purpose. So there's really more than just the 12 notes that we all love, you know. And so that's one thing that is important to note. And yeah, if you don't know him, check him out. He's amazing. Yeah. So in some more background that you need, that we need for today's talk, is, for example, the Weber-Fechner law. So you know that maybe that a lot of signals that we process are we perceive logarithmically. So heat, but also loudness, and especially also frequency. You know that, for example, well, 440 is an A, 880 is an A, but then it's not 440 more, but twice as much. So it's always twice as much that's an A. So you're perceiving frequencies logarithmically, and that amazingly really goes with most of the signals that we all perceive in our brain. Another important aspect is the aspect of phase locking. So phase locking basically means that the neurons, they fire they lock into the waves that you perceive in the brain, or in for example, the hearing. And well, I will not go into details about this phase locking, but this phase locking is an explanation, for example, for why on a telephone you can actually disregard the lower frequencies and still hear the lower tones, even though they are not there, they are not being transmitted. That's phase locking, but it's also the basic principle why we have pitch detection. So when we hear a complex note, you can hear a certain pitch, even though there are lots of pitches in a tone, in a complex tone. And then it's also an explanation for the just noticeable difference in a way. What is the just noticeable difference? It's something that the psychoacoustic scientists, they think about a lot. And it's when you hear one note and another note very close in pitch, there will be a point where you cannot differentiate between those two notes. And so there's an experiment that they like to do. They give you 20 pairs of notes that are close to each other. Maybe they're equal, maybe they're not equal, but you always have to say which one is smaller, which one is bigger. And when you do that, obviously, when it's very much smaller than the reference pitch, you will be able to differentiate it. So you will not make mistake. But when it's bigger, you will also not you will also not be confused about it. You will be able to differentiate it. But when they are close together in this range, then you don't know for sure. Some people can differentiate pitches better than other people. But this just noticeable difference is also an important part of music. Why? Well, when you hear people playing tunes out of tune, you can still enjoy it a little bit. So those are basic concepts from neural coding that I just wanted to give you in advance that will come up a little later. Next thing is, so why we have 12 notes in the scale. It's basically a compromise. And it started early on, well, that you actually had different tuning systems. I'll get to this here. It developed over time. But so where does this come from? Why do we have the need of a discrete set of notes? That's basically because you have overtones, and most instruments, Western instruments, have a harmonic spectrum, and that's basically due to this this picture where you have when you have a string, it can vibrate in very in these frequencies and not much more. It's not always exact, so it's always a little different, but that's basically all the instruments. They have something like this harmonic series, and then these things, they overlap, they interfere with each other, and you can, well, you get phenomena that are called beating speeds. So when you have notes that are very close together, you can hear beats. If they're just 2 hertz apart, you hear a beat that's about 2 hertz, and so that's the interference. And due to these interferences, people had to, well, choose notes that sound good. And let me show you a few different sound examples. So there are, well, there's our 12 tones equal temperament scale tuning, but then there are 2 other tunings that are kind of popular. Obviously, we don't really use them, but they don't sound too bad. So let me show you, because it doesn't make a if you listen to this, there's not really much of a difference. Okay, what's that? It's 19. Okay, and then the last one, that actually sounds best. Okay, so that's just a different tuning system, equal temperament, so they have their equal distances apart, and then there are also other timbres. So when you have the harmonic spectrum, you can move the tones a little bit, and so that the spectrum is a little stretched, and so that's something that William Cetheris thought about and compared stretched timbre with stretched scale. I will not do this right now, because otherwise I will not get to the fun stuff. But this might be interesting, and that's why, let me just show you what this is, and you can, I think the sound will be enough of an explanation. Okay, so this is something that just went up, right? But I'll start this again. And it starts exactly where it ended. So this is known as the Shepard scale, and it's very simple sound illusion, acoustic illusion. But why I'm showing you this? Well, first of all, it's pretty cool, and it's been used in movies. For example, The Dark Knight, or well, there are a few other movies by Nolan where he used that. But the point is that even with this kind of a scale, which is really kind of odd, you can still listen to tunes and they still sound totally fine, even though they might be a little boring. So there's this Bach played with a Shepard cembalo. the whole tune, but it sounds totally fine, perfectly fine. So why am I telling you this? Well, there are a lot of things out there that we have to consider when trying to model music. And we have to see, well, how can we simplify the whole point? So this fact that basically the music theory sounds the same, even if you have a circular scale, is something that we should consider. So there's some other tuning systems there that are important and related to the spectrum. But let me now go to what I really want to talk about. And one aspect of music perception that is really the first aspect that you run into is is consonance and dissonance. And there are two different kinds of consonants that are very related, really more or less by accident or due to by physics. There is something called roughness. So when you play two notes very close together, then you hear these beatings, right? When they are very close together. But when they go a little further away, you can still not differentiate those two notes, but it sounds bad or it hurts in the ear and it sounds unpleasant. That's a kind of dissonance, and it's also known as roughness or sensory dissonance. And then when you move them apart some more, then you can actually differentiate those two notes, and so that's roughness. The other thing that really music theorists talk about when we talk about cadenzas, we have a 2-5-1 cadenza, and it resolves, the tension resolves. You have you have a more consonant chord in the end. That's something also known as harmonicity, and it's a different kind of consonance. It's not 100% clear what drives that, but one explanation that sounds reasonable is something called periodicity. And you see a graph of periodicity for two notes up here, but let me explain to you what periodicity is. When you have three notes play together, you have, in this case, a major triad. This is the lowest note with the longest wavelength, the lowest frequency. Here you have the biggest frequency, and you play them together. Then with relation to the lowest note, at some point they will match up. And that point, when you count how many periods we have, is called periodicity. Very simple. And that is one way of measuring consonance with respect to music theory. So this has been studied. This is something that I created because based on this work by Stolzenbock, I tried to smooth this out because obviously when you hear two notes together, you move them back and forth. It doesn't change discretely. Okay, so those are perceptive qualities that I would like to be able to study within a model. And so now we get to the geometry part, and we start with the geometric construction. So how do you do that? Well, it's really not that big of a deal, but if you have four notes, you can put them on this, in this line, and obviously you can switch them around. It doesn't really matter in which order you have them. So you basically have an equivalence class. You have R4, four notes. You can switch them around by the symmetric group, and that's, well, one way of modeling four notes. That's something that Timochko did in 2006, and he published that in Science. Somehow it was very popular at that time. What he did also, he modeled out this real line by 12, so modulo 12, because we have this circular way of doing things, similar to the Shepard scale. But we will really look at R4 instead. And instead of just looking at four notes, we also might like to, well, first of all, we might have the situation that we have two notes that are the same. And we also want to identify these. And also we might have, well, four notes and they changed into five notes, or rather four notes can be viewed as five notes, where one note is played simultaneously. This gives us a stratification of a space. Okay. So it's a nice way of modeling it. It's not really a difficult way, but let's take a look at what the space actually looks like, because it's geometry. So let's look at this second stratum. What we do is we identify 2, 1, and 1, 2. And what this does is that you have one line, for example, sitting in here of the nodes that are basically, well, the same PP. And then because of this identification, you're basically looking at this space right here. That's our stratum C2. That's the space of 2 node chords or diodes. And let's look at the space of C3 for a second. So when you have, for example, the 0, 0, 0 node here, or chord, you can see, compare it to the 0, 1, 2 chord. And one thing that is important in music theory is something called voice leading. And what the music theorists like to talk about is something called a voice leading distance. The trouble is the voice leading distance is not really a distance. It doesn't satisfy the triangle inequality. But the nice thing about this geometric description is that you actually have a distance that satisfies the triangle inequality. Let me show you what problem we have when we do this. Yeah, when we want to know what the distance is from here to there. Well, the easiest thing is to say, well, the difference between 0 and 0 is 0, between 0 and 1 is 1, between 0 and 2 is 2. So altogether, the distance is 3. But the trouble is when you do that, and you look at, want to see if the triangle inequality is satisfied, well, if you insert this node right here, then the distance between these 2 nodes and between these, or 2 chords and between these 2 chords is smaller in sum than that distance. Well, the nice thing is now that we have this geometric description is that you can, that we have a Riemannian metric on this space. The Riemannian metric allows us to have a geodesic distance. And the geodesic distance, it's basically the shortest path from here to there. And the shortest path from there to there is not, well, in this case, not the direct path, but basically this path where you go here and then there. So the geodesic distance in this example will be the minimum of the distances when you look at the sum where you plug in various p's. And what you see is, well, there you actually get a 2. So the geodesic distance is 2, and that satisfies the triangle inequality. So now you have, you have a Riemannian metric. You can actually worry about differential geometry. That's the first thing that you really have to do. And well, when you, for example, consider periodicity, you get nice pictures like this. Okay, maybe it will eventually. So I'll talk a little bit about it. It will help understand what happens when you move in the space of chords when you look at the music. And for example, what you see here is you see a major triad, but a different. So it's a CFA, and it's this chord right there. And you see these blue things. They are very consonant, or they are very low periodicities. So you can see that along this line, those are all just diodes, right? Really. So you have the 5th here, the 4th here, but then you have these other spots, and those are all triads, major triads or minor triads. So, but it's already nice, and you can see this is a contour plot. It's a smooth. It's like a height function, and you can really look at paths and differentiate these paths. Maybe it will be helpful, maybe not. But let's just go on, because there's one thing that's really quite interesting when you look at a particular chord, namely the tritone. The tritone is very dissonant, very, very dissonant. Well, it's not that bad, but you can worry about where it might change to. Oh, one way. What's the best way of resolving? Okay, and this, and then last one. Okay, well, it doesn't matter. You can listen to it later. There are 6 different ways of resolving this chord, and there's really one that, or two that are the best ways. Moving inward, so moving both notes inward or outward. And this actually corresponds to, in the end, to a very common 5-1, so a resolution, when you consider it in context. And that's kind of interesting. And I must say that's very interesting when you look at, okay, let me tell you, this context is basically when you put it in a tonality context, then moving inward or outward really takes it to a different place. It doesn't sound bad, but when you have it in a certain tonality, moving it inward or outward really matters. It doesn't sound, as I said, it doesn't sound bad. It sounds still consonant in a way, but it's like changing the direction. And that's precisely what geometry will help you talk about: direction, curvature, whatever. Okay, that's one. Oh, no. Maybe I meant this one. Ah. Okay. Okay, that sounds. So which one sounds more reasonable to you? So whoever thinks 8 sounded more reasonable, hands up. Okay, whoever thought 9 sounded more reasonable, hands up. Okay, it looks like it's a little less, but whatever. It's not very, it's not a proof, but in any case, it's the same chord in the end, but you have a different tonality. Okay, we are at the end. Okay, so. So it's just, well, you will have to talk. You have to see how you want to. Yeah. So you have to. You have to study this, right? And geometry helps you with that. You can talk about tension and release. You can define something that sounds reasonable, transitive periodicity, using the periodicities that we have, something like that. And that helps you get into what music sounds like. And then what you can also do is, for example, look at directional derivatives, for example, of periodicity. So if you want more details, you can go to this preprint here, and I'll be happy to answer any questions that you might have.